Run. Let's come back. Lots of good questions over the break and lots of people asking about exactly what we're about to do next, so it's very timely, about how to do unit testing in task 2 and what a unit test means and how the assert thing works and all that sort of stuff. So I want to tell you about something called extreme programming, just very quickly. It's this concept that we'll be talking about from now on. Now I know it's ludicrous to think about extreme programming. It's a ludicrous combination of words. And I did see somewhere once on the internet extreme ironing. Has anyone seen that? Yeah. Where people jump out of a plane and they have to iron a shirt before they hit the ground. It's the most awesome thing. Has anyone seen that on YouTube? Yeah. Can someone post a link? Because it just makes me laugh. So extreme programming is as ludicrous as that. What extreme programming is though, is I've got to say, it's a methodology for writing programs that is sweeping the commercial world. So certainly when you're out in industry as a programmer, you are bound to, unless things change again, come across at some stage people doing extreme programming. And at the moment, it's the exciting new places that are doing extreme programming, and it's the old traditional places that are doing it the old way. So it's sort of the current new thing, though it's not that new, you know, it's been around for a long time, but it's very exciting. If you're doing software engineering here, you're probably going to be taught a lot about the waterfall method. Have you already heard of the waterfall method? Okay, let's go. Waterfall method. It's very exciting, the waterfall method. Here's how it goes. The waterfall method is, you approach a problem and you don't know anything about it, so you gather a whole lot of information about it. And that's called the requirements. You gather requirements. And then you sit down and do lots of planning. And that's like design stuff. And then you like prototype a whole lot of stuff. And then you like write your code, and then you like do all this testing on it. And then, because it doesn't work, you go back to the beginning again. And you keep doing that over and over again until your project runs out of money. Now, most software projects in the real world fail. It is amusing, but true. And it's a secret we don't often tell people. But most software projects fail. I mean, if you ever meet someone on a big project, you'll say, how's it going? And often they'll say, good, it's exciting, we're in the opening stages. Or they'll say, oh, I'm looking for a job somewhere else, it's not going well. And I've spoken to friends who have done lots of big projects, flown over to Switzerland to set up stuff for the stock exchange in Switzerland, or some place like Switzerland. And they spend lots and lots of money on it, and then the project failed. And there's famous projects in Australia that have failed that are so funny. And often I get people coming to my security course that work for those companies or the famous projects, and you can say, I won't even say what the projects are, but someone will say, I'll say, what company are you from? And they'll say, oh, I'm from Westpac or something, and you'll say, oh yeah, tell me about that, and they'll go, oh. It's okay. So the idea is most software projects fail and they absorb huge amounts of money. Huge amounts of money before they fail. Now, studying why software projects fail became very interesting. And a lot of people obviously spend a lot of time on that because it's not good spending heaps and heaps of money. And I've had my share of failed projects, I've got to say, and I bailed towards the end. When you just think this isn't going well, I'm bailing, boom, boom, parachute. There's lots of reasons they fail. Now, one way you might be able to fix it up is by more strict adherence to this process. Maybe we didn't gather enough requirements properly. Maybe the design wasn't rigorous enough and we didn't have enough good people. And then all the good people left about halfway through. I don't know why. And okay, so maybe you could fix it up. But some people thought of another way of doing software. And they described this way, the guys that thought of extreme programming have this little famous analogy, which is, this is like a cannon. Okay, like we've got here, we've got, what have we got? We've got a battleship. It's one of Napoleon's battleships. I'm very anti-French today, aren't I? I've been watching the hornblower films, and those French are so villainous. Okay, so we've got this French battleship here. And then we've got over here our land station, our fort, with a cannon. Now we could spend 5 million years calculating tables and trajectories and building the world's most enormous cannon and calculating everything exactly right and doing all these things, and then fire one perfect shot. Boom, that sinks it. The problem is, we might run out of money before we finish building the cannon, or the ship just might sail away before we finish building the cannon. Or, and I just don't want to admit this could ever happen, what if we, and despite of everything, So the people in extreme programming saying, look, rather than doing everything in one big shot and trying to make it exactly perfect, so when it fires, you're absolutely sure it's going to be correct and hit the thing, and everything's fine, and all this work and planning is going to be powerful. I said, why not just have a little cheap thing that does bugger all, and just keep firing it until you get there? In other words, why not we just try and see how we go? And we might say, oh, it didn't hit it, but we could raise it a bit higher and we might hit it. Oh no, a bit lower and we might, okay. So this idea of extreme programming is this. Someone gives you a problem, and you look at the problem and it's a complicated problem, and it has hundreds of things you want to do. Instead of trying to do them all and build the world's biggest cannon, you say to the person giving you the problem, well, what's the most important thing about this problem? What's the thing that would make you happiest if we did? Just pick one of them. I know there's 50 things. I promise we're going to do them all. We all know we'll run out of money before we can do them all. But instead of stopping short on all 50 and it being a complete failure, we think, well, why don't we try and get 25 of them done, and just 25 we won't even attempt, and that way we'll have a halfway success. So we say, you tell me the most important thing, and then we go away and we do that most important thing and we get that working, and it's something small and simple. After we've got that working, we show it to you, you use it, you're happy, and then we say, now what's the next most important thing you'd like? And constantly we're going back to you, asking your input about what's important and what's not important, and we slowly converge on the perfect solution. And maybe we never ever get there, because in software maybe you do never ever get there with big things, but we know at any point we've already got a lot of the way there. Now we tried to do that with the first task. Could you see that? We wanted you to write something that solved the first 10 numbers, and then solved the first 100 numbers. And already you're getting marks for doing that. You could have gone away and thought, I'm not going to do anything, I'm just going to at the end reveal a perfect solution that does all the numbers. And maybe that would have worked and you got full marks. Or maybe there would have been a mistake and you got nothing. And we said, no, get it working for 10 numbers, then get it working for 100, then get it working for 1,000, then get it working for 1,000,000. So there were a series of goals that were somehow all related. Now, of course, in practice, your goals might not all be related. It might be get your system so it can do debits and withdrawals, then get your system so it does the tax calcs, and get your system so it does this. So you might just add new functionality that's not related to old functionality, or it might be increasing the size of the old functionality. This is extreme programming. Now, extreme programming is a crazy sounding idea, and there's this whole methodology that goes along with it to sort of make it work. One of the things is, after you think straight away, an experienced programmer, anyone who's an experienced programmer in this room is probably thinking, I can see a problem with that straight away. Because if you write the solution for 10, you're going to have to change that to get the solution for 100. You would have been better off writing a more general one initially that would have done the 100. And in fact, you know, then you're going to have to change that for the 1,000. You would have been better off writing a more general one that, well, come on, let's face it. You'd be better off to write a more general one that does all the numbers up to 1,000,000,000,000 and just get that right. And now, oh, you've suddenly gone back to the old way of thinking. You can see how we drift back to that all the time. So in extreme programming, we say, no, we're going to write the one that only does 10, knowing full well that later on we might even have to throw all that away to write the next one. Now, anyone that is a programmer hears that thinks, I don't want to do that because I've put all this effort into debugging my first 10 or my first 100 or my first 1,000. I don't want to throw that away and hit all those problems again. That's nightmarish, that's confusing. All right, now this process of changing your code to add the new functionality is called refactoring. So you get your existing solution and you somehow have to change it to do a new solution. That's called refactoring. And it's a scary thing to do, and no one ever wants to have to refactor. One of the principles of XP, extreme programming, is be bold. Don't be timid. So you are not frightened of refactoring. You say, okay, we've got it all working fine. The next task is to do that. Oh, okay. We're going to have to change everything we've done. And at that point, you look up and you grin. Okay. You work in pairs with someone else, so you're always giving each other moral support. And every time you do something, you write a test to test that it's correct. And these tests are called unit tests. Each of them tests a little thing, a little unit at a time. As you build up your project, you write more and more unit tests. So by the time you've done the numbers up to 100, you've written unit tests testing the numbers up to 100. Then after you've refactored, which is sometimes scary, but you're brave about it, what's the first thing you do? You run the old tests against what you've just done. And if it's all correct, you go, whew, the refactoring worked. And if it didn't, well, you've got this great enormous bank of tests you've already developed, and they quickly throw up the errors and you quickly change them. A brave XP person can refactor in an afternoon. They go, okay, I've got everything working. Now I'm going to the next stage. Oh shit, I've got to change the data. Oh damn, I've got to change the data type. And I've got to change this, and I'm going to have to change some array loops. I'm going to change 50 things. You just go in there and you change it. You're not frightened. You don't care, because you can always go back. You haven't lost your old copy. Because at the end of doing all that, you go, okay, now run the unit test. And either, ba-bing, they all pass. Ah, the refactoring worked. Or one of them fails. And you go, damn. But the failing test gives you a clue where the mistake is and you go and fix it up. Does that make sense? So the idea with unit testing is you constantly add to your tests. You have a suite of tests and you never take a test away. You just add more and more tests on. And whenever you do anything and make any changes, you just run the tests again. I like imagining it as like the tests are a big red button. And whenever you do any change, you just go, hit the button, and 100 tests run past, and it goes, at the end, hopefully, all passed. And you go, ah. Now, I've said before, I think programming is a psychological thing. And it's fear that stops you doing stuff, and tiredness and depression that leads you to making mistakes. This unit testing is the biggest psychological shot in the arm you can ever have. Because whenever you do anything, you push a button, and it says, all done. And the feeling you get when it says all passed is so good that like every minute you're just getting this great shot of adrenaline going, woohoo, I'm so cool, it all works still. You're never afraid of breaking anything because you've got tests that test every single thing. Does that make sense? Okay, so how do we implement tests in C? In C we're going to implement all our tests using asserts. And you're going to sort of see it in the tutes and labs this week. We're not testing any side effects in this assignment, so read and show grid are not going to be tested. We don't care even if they work or not, I guess. We're not going to test them. Read and show grid are for you. You're going to need them to do your testing. We don't care about them. Read and show grid are the only ones that have side effects. All the other functions just deal with C directly, changing memories, locations of variables, and so forth. So how you do it is you write a test, and in your test file, what is it called? I can't even remember the top level thing. It's called test Sudoku grid. Is that right? And that's because whenever I write a file, like I've written a file called Sudoku grid.c, whenever I write a file, I instantly write another file called test whatever I wrote.c. That's my test file. Now, Sudoku grid.c doesn't happen to have a main in it, does it? All right, so we've got another function somewhere else, another file somewhere else, which is main.c. And that contains a main function. Oh, it doesn't have to be called main.c, but suppose it does. Main, those two things, blah, blah, blah. The first thing my main does is it calls, what's it called? The function. I think I normally call the function the same as the name, so it's probably called test Sudoku grid, is that right? It calls test Sudoku grid, and then it does whatever it's supposed to do. So whenever I run my program, before it does anything, it runs all the tests. Now I don't take that line out, I don't do anything with that until just before I hand it in. And just before I hand it in, I might comment that out. So my test doesn't run every time the program runs. Some people actually ship their code with all the tests still active in it. You can do that. Yeah, I have to obviously have it so it doesn't print anything out if there's a mistake. But normally what we'd do in this course is we'd comment the tests out just before submitting. But until that instant, every time we run the program, it would run all the tests first. Now, and then it does whatever the program does. This is the solve Sudoku code you've already seen, happens here. So where does this function defined? It's defined in the file called test Sudoku grid. So there's a function here called void test Sudoku grid. What's that? Oh yeah, we'll look at .h's in a second. I'm just at the moment looking at where all the files are and how the files will behave. Now test Sudoku grid, for me, does nothing except call a whole lot of tests. It calls, what's the first test I'm going to write? Maybe the first function I'm going to write is look, your assignment is to write a whole lot of functions. Which function should you write first?
It's legal.
The easiest one. We're going to manage our emotional state. What's that? Clear cell. That's the easiest one. So I'm going to write a function here called test clear cell. That's the first thing I'll do, because I reckon clear cell is the easiest thing. And test clear cell has no arguments. And then down here I'm going to write test clear cell. And what's test clear cell going to look like? Let's write it. Now notice what's going to happen is as soon as I run my program, it's going to run test Sudoku grid. And as soon as test Sudoku grid runs, it's going to run test clear cell. Now what test clear cell is going to do is, if everything's okay, it's going to do nothing. And if there's a problem, it's going to abort the program and tell me what the problem was. So here's test Sudoku grid, test clear cell. It's going to do something like, well, let's create a Sudoku grid. Sudoku grid sample. And then it's going to go, what am I going to say? I'm going to say clear cell 5. And then I'm going to say, what am I going to say? Assert, not get cell, because I haven't written get cell yet. Sudoku grid. Oh, what's it called? It's called sample. Sample 5 equals empty cell. Now what that does, if you remember how asserts work, is if sample 5 is equal to empty cell, it just passes and it's completely silent. And if there's a problem, it kicks up a message and tells me what's gone wrong. And that's my first test. And then I'll put another assert, and another assert, and another assert. And I'll do all this crap in here, this testing clear cell. And then when I write the next, and then I'm going to write my function called clear cell. And as soon as I've written my clear cell function, what am I going to do? I'm going to write run, and it's going to run my main program, which will run my test Sudoku grid, which will run test clear cell, and it will print, oh, I forgot to put the best bit in. At the bottom of test Sudoku grid, what do you put down? I've got test clear cell, and then before anything else, I printf. At the very end, I say all tests passed. And because I'm so happy, I always put an exclamation mark there. This is at the bottom of all the tests. Yeah. And if it gets through all the tests without tripping an assert, this will print out. So the first thing I do is I write test clear cell, and then I go run. And it runs it, and it prints out all tests passed, and I go, woohoo, clear cell's done. And I move on to the next one. Does that make sense? And I write the next one, and maybe I'm writing set cell. So I'll write test set cell down here. And then I'll write test this and test that. And I'll just keep going like that, writing more and more tests. And the sequence is always, I write the test first, because that makes me think about it, and then I write the function. And then as soon as I've written the function, I run the test. You don't want to do it the other way around. If you write the function first and then write the test, you'll find your test looks exactly like the function you've just written, and you're not testing anything independent at all. Yeah? You don't want to, if you write a test knowing what you've already done, then any mistakes you've made in the function, you won't think to test for them because you didn't think about them when you're writing the function. So you write the test first, then you write the function. Does everyone get that right? Yes, question?
What happens if we think we want a test that doesn't involve asserts, that does something a different way that you couldn't really do, like with asserts at all, or maybe not nicely?
Hypothetically?
I don't know. Just maybe that happens.
Can't think of it. Can't think of an example. If you can think of an example, come back to us with it. But you should be able to do everything with asserts.
Can't we just put asserts in the functions when we test
Your function should have asserts in them to test the preconditions, but that's not a unit test.
Can't you put, to test it, can't you just put the assert at the end of the thing, like in your main? Why do we need to like put like a new test like function in the test?
I don't think I'm understanding your question.
Like, why can't we just test it in the main?
Oh, why can't you just test it in main rather than testing it in a function called test Sudoku grid? Well, you tell me. Oh, but think about it. I bet you do. Does someone know? Why aren't we testing it in main?
It just makes it more complicated.
Yeah. What's main do? Main's the main function. If you want to test some stuff, where should that be? It should be in a testing function. You're going to write, for every file you write, you're going to write a test file that goes along with it. Your main has nothing to do with these files. Does that make sense? Your main just does the big job. Main's the big kahuna. It's like the director at the top. In top-down design, main doesn't worry itself with all the fiddly details, remember? Main just chucks a whole job over here and a whole job over there. And we get little underlings to deal with those jobs. It's those underlings that should test what they're doing. The director doesn't know, oh, the cubicle in block 15 should be painted light green. And the big director at the top shouldn't know that stuff. So in every file we write, we put a test file that goes along with it. Now, how we're going to mark your assignment is we're going to mark your file, your Sudoku grid.c with our own test Sudoku grid.c. Does that make sense? We're going to run our own unit tests against your functions. So what's the point of you writing unit tests? You tell me. We're not going to use your unit test to test your function. Why do you want to write the unit tests? Because they make your program work. They help you write your program. What are we going to do with your unit tests when you hand them in? Are we going to ignore them? No way. We've written 50 diabolically broken Sudoku grid.c's. And your test Sudoku grid.c's had better find every single one of them is wrong. and we've written 50 completely correct ones. And your test Sudoku grid had better find they're all completely correct. Does that make sense? So we'll run your tests on our code and our tests on your code. So there's none of this, oh, I won't test you too hard, don't worry about that. Because if you test yourself, you never test yourself very hard. Can I say, in the final project, your tests will not be applied to your own code. Whose code are they going to be applied to? Your opponent's code. You're going to be competing in a competition, and your tests are written against their code, and their tests are written against your code. And you're going to hope you crash their program. Yes?
But I'd like the tests just like individual cases, for example,
Yes.
just work one case.
Yes.
So if you give us
This is a good question.
if you just give us like 50 random cases, then
Yes.
how are our tests going to find? They're going to find which one's right and which one's not.
Oh yeah. I mean, how are you going to test us in the final project? You mean? Oh, when we give you the broken ones? Yeah, that's a good question. That's a good question. Can I rephrase that in terms of task 1, so maybe make it clearer? Suppose for task 1, we had given you 50 broken Bjorns, and you had to find the mistake. And suppose they were broken in this way. Bjorn is completely correct, except for the number 632, in which case he prints the number backwards. That would be unreasonable for you to find, because you would have to test every single number to find something like that. So we will not be breaking our code in that way. We'll be breaking our code in the ways that we think programmers would break code. So our loops will be off by 1, or extreme cases might not be counted properly. So we will make what we think are plausible programming errors. We're not going to just say the program's completely correct except for one case, because, of course, randomly you could never find that case. Does that make sense?
Yeah, but for example, say for that one.
Yes?
So say for that one it sets like square 5 to 0.
Yes?
And say we do that for like maybe 10 cases.
Yes.
What happens if you give us like a case it's not those 10 that we've had unit tests on?
Okay, I think what you're saying is, what if we write a Sudoku grid that's completely correct, except cell number 16 never works? Any value you stick in cell number 16 doesn't work. And suppose you've tested 10 cells randomly here, and you didn't test cell number 16. What am I going to say to you?
Test all of them.
Yeah, you've got 81 cells to test. If you don't test all of them, what are you thinking? It's like saying, I've got a car, it's got 5 gears. I'm going to test 4 of them. Because you might as well test 5, it's conceivable. So yeah, you should check every single cell. Absolutely. Because 81's not a big number. But you don't have to test every single input number to be on, because that's 3 billion. That is a big number. Yeah. So whenever you can, write programs that go through looping and testing every single case. Yeah. We're not going to do anything that's crazy, but we're going to put diabolical programming errors in there that we think are legitimate programming errors. We may well get our broken solutions from the submissions we get to the assignment. Does that make sense? So we might find some student has a program that fails in a particularly interesting way that our unit tests happen to pick up. And we might think that is a classic programming error. I wonder if anyone has got a unit test good enough to spot that. And we might say, oh, we'll use that one as a sample.
You get extra marks if you make a really good error.
Do you get extra marks? I like the way you're thinking. You get extra marks for that suggestion. That's cool. He said, do you get extra marks if you have a really good error? If you have an error that makes us laugh, yeah, you can have a Mars bar. Absolutely. Yes, Joel.
You said to ask the question again. If you
Yes.
have get free cell,
Yes.
someone searches for the free cell from the front,
Yes.
another person searches for the free cell.
Ah, yeah, thanks. That's cool. All right. Some of your functions in this assignment are deterministic. So clear cell, it's really clear what that has to do. It has to take a particular cell and set it to a particular value. And some of the functions are not deterministic. The ones that return true or false, for true, they can return any number, not just the number 1. The one that says get a free cell can return any free cell. So can you write a test? Suppose your get free cell finds the first available free cell. Should your test for get free cell check that the cell it returns is the first available free cell? No. You're testing something outside the spec. The spec does not require it to return the first available free cell. It requires it to return the first free cell, a free cell. If you wrote a test that it was only passed if they returned the first free cell, you would have actually written an incorrect test. And when we're marking your tester, you would lose marks. And you'll find that happens. It might not be clear now. Let me give you an example that'll make it really clear. We're in the project. We're in the next assignment. We're running your testers against other people's code. You hand your code in and it's quite correct. And you made an arbitrary choice somewhere. Someone else made an arbitrary choice in their solution and they chose to do the other thing. You know, maybe your function could return 1 or 2 and in both cases it would be correct. They chose to return 1, you chose to return 2. Your code fails their tester. Who loses the mark? You or them? The tester is going to say, but my function returns 1. And this person is going to say, well, my function does a legal thing. Who's correct? They're both correct. Who loses the mark? The tester. We actually have a system called the spot system. And what happens is when your program fails a test, you both get a spot, which is a blob against your name on the internet. We control the internet on a web page. And then you have to resolve the spot between you. You have to work out who was right and who was wrong. If the tester had an unreasonable test, if they were testing for something outside the spec, the tester should accept the spot. If your program made a legitimate mistake, you should accept the spot. If you can't decide it, then you ask your tutor to arbitrate. And your tutor arbitrates and gives whoever gets the spot 2 spots. Does that make sense? Because there's no reason to ever go to arbitration. It should be clear in every instance who gets the spot and who doesn't. All right, now is everyone clear about, did that answer your question, Joel? Yes. Okay, so we talked about XP. Relaxed style. I mentioned in the spec, your unit tests can be written in a more relaxed style than normal. This means the style guide doesn't strictly apply to the unit tests. Instantly now people have all got excited and want to use switch and all sorts of crazy things in the style guide, in the unit test. No. All we mean is unit tests don't always look exactly like a program. You should strive to make them as clear as possible, but necessarily they might involve some magic numbers, like the one here that tested 5. If we want to test an arbitrary cell, we'll just test 5. It's a magic number. You know, maybe you're going to hash define that and maybe you're not. It's up to your call as to what's clearer. So we're a bit more relaxed about magic numbers in unit tests. Sometimes your tests get quite long. Wherever possible, you should break them into sub-functions, of course, but sometimes it's quite natural to test this, then test that, then test that, and have a long function. So we're slightly more relaxed about the length of functions in things. Still strive to be clear, but we regard long unit test files as still clear, and we regard some magic numbers as quite acceptable. That's the relaxation. Does that make sense? Yes, question?
Can we use the random number libraries to,
Oh, can you use a random number libraries? No, not yet. But if you ask me to do an extension lecture on random number generation, you can. Yeah.
Can we do an extension later?
Yes, we can do that. And after that, you're welcome to use those random numbers that we generate that way. Yes?
In the test cases that are to break you,
Yes?
do you by any chance have a Sudoku grid that has like an A in it or something like that?
Oh, no. Good question. When we look at the assignment in the .h file, you'll notice it says every now and then, you can assume, you can assume, you can assume. We can't test anything where it said you can assume. So if it says you can assume it's a legal grid and all the numbers are in a legal range, we can't test what your program does for an illegal grid because you're allowed to assume that it's legal. Does that make sense? That answers your question? Yeah. So anything you can assume, you're safe. What should you do, by the way, when we say you can assume something?
Well, if it's not something, you just make it a clear cell.
Yeah, no, but there's something you should do. Whenever I say you can assume something, you instantly have to assert it. You assume it and you assert it to document you've assumed it. That's not a test, that's just checking the input assumptions are held. Yes?
Does the same hold for the programs that are intentionally broken, that we're supposed to discover they're broken?
The programs that are broken,
Will not have A's.
let's think. No. Let me be really precise about what I mean. It's not programs that are broken. Your unit test tests the functions, and there's about 7 of them or 6 of them you've got to write, aren't there? Clear cell, set cell, get cell, is legal, So there's a range of functions. Your programs test those functions. Your unit test tests those functions. When we give you something broken, what we'll give you is a range of functions, and one of those functions won't work correctly. Won't work correctly means that given a legal input, it will produce an incorrect output. So if you test it by giving it an illegal input, it's you that's wrong, not the program. Because if the program says, if the function is told it can assume something, and the tester gives it an input that doesn't assume that, then the tester is wrong. It's like me saying, throw anything, any paper aeroplane at me you want, and I will catch it. And someone throws a sword at me. Whether I catch that sword or not, I have not broken my promise. My contract is, you throw a paper aeroplane at me, I will catch it. So testing me by throwing things other than paper aeroplanes is not really a fair test. Does that make sense? So do not test things outside the spec, because the program is entitled to do whatever it wants if it's outside the spec, and it would be correct. Does that answer the question? I forgot who asked it. Was it you? Yeah. Yeah. Any more questions? Is it excellent questions? Is that a hand? Or? No. All right. All right. Well, so we're nearly there. Multifile projects. Oh, merge and asserts. What does that mean? Oh, well, someone, for the lab this week, you've got to write a merge. And someone said, what happens if the inputs to the merge aren't sorted? The specification for merge said, you can assume the inputs are sorted. So what does your function do if they're not sorted? Who cares? Do whatever you want and you'll be correct, because you're told you can assume that it's sorted. Does that make sense? If you get something that's not what you're told you can assume, no one is going to say you're wrong no matter what you do. You are only wrong if you get a function, two inputs that are sorted, and you produce an output that's not sorted. Yeah, there was a question here. Yeah.
Just extending on my previous question.
Yes.
So if you have a function like isLegal, does that mean we have to test every single case that is possible for isLegal? Because isn't there going to be like millions and millions of cases? So that's what I was getting at, saying, because we're only going to test a fraction of the possible cases, what happens if the function that you give to our tester produces a wrong input in one of the cases that we didn't test, that our tester didn't test?
isLegal only has to test 27 things, so you can test them all.
Is it?
Yeah, isLegal has to test that every single cell in the column is different, every single cell in the row is different, and every single cell in the grid is different. There's 9 in each of those, 3 overlap, so it's 25 different things. So yeah, you should test every single one.
Yeah.
Absolutely. Yeah. Okay. Multifile projects. What we've got now is our assignment fills up many files. It doesn't just fit in main.c. There's a main.c, a Sudoku grid.c, a Sudoku grid.c, a test Sudoku grid.h, and a Sudoku grid.h. There's 5 files. What's the relationship between these files? Okay, main.c, you write yourself to do your testing and to check everything out. You don't get to hand it in. So you just write it to help yourself. It should call your tester and do all your stuff. Yeah, you can do it. No, your test Sudoku can't have a main in it. No.
Well, your Sudoku grid would have a
Well, all right, let me tell you what happens. When you write a program and you split it over 3 files, what does the C compiler do? It compiles each of those separate files. Then it hunts through those 3, and what's it looking for? A main. If it finds 2 mains, what does it do? Freaks out completely. When it finds the one main, it then looks at all the functions that that main calls. Suppose it finds you call a function called clearCell. What does it go do now? It hunts through each of those 3 files for clearCell. If it finds 1, how happy is it? Woohoo! If it finds 2, how happy is it? If it finds 0, how happy is it? Yeah, oh no! Yeah, it throws an error. So the idea is, each function just lives in one of them, okay? Don't put it in multiple ones or it'll get confused. When it just mushes them all together and hunts for it, so it'll find the stuff. The danger isn't that the compiler's not going to find the stuff. The danger is you're going to have a function in this one called clearCell, and you're going to use a function in this one called clearCell, but this one's going to return an int and expect an int, and this one's going to return an array, a char and expect an array. The compiler's pretty stupid, and it's not going to detect that the clearCell you want doesn't have the same type signature as the clearCell this guy's providing. It's really stupid. It actually has no idea at all. So you've got to make sure that when you call a function, you're expecting the same type signature as when you provide the function. Now, if it's all in the one file, it's easy to do that because at compilation time, you put a prototype at the top and the compiler tells you if your function doesn't match the prototype. So you're cool. But in multiple files, you don't get that benefit. So what we really want is when we have multiple files, we want the prototypes for all the functions at the top of every single file. And if the prototypes are at the top of every single file, then the compiler is going to tell you if the function you're using doesn't match the prototype or the function you're declaring doesn't match the prototype. So how do you put the function prototypes at the top of every single file? Well, you could type them in at the top of every file, but what's the problem with that? It's a waste of time. If you change one, you have to change it everywhere. You'll probably mistype one of them and it'll say this here and this here. You really want the same prototypes at the top of each file. How could we do that in C? Make sure the same prototypes are at the top of exactly every single file. We hash include them. So what you do is at the top of every file, even step ahead of that. What you do is you put all your prototypes in something called blah.h when you write a file called blah.c. You put in blah.h the prototypes for all the functions in that file. And then you hash include blah.h and blah.c. And you hash include blah.h in every other file that uses any of those functions. And then everyone's got the same prototypes and everyone matches, everyone's happy. You don't hash include the .c file though. If you hash include blah.c in all the other files, then you're actually including those function definitions in each of those files. And now you've got to have a function that's defined in multiple places, and when the compiler comes to stick it all together, it'll find 2 or 3 versions of that function. And it won't know they're all the same. It's stupid, and it'll get very upset. So we never hash include a .c, we just hash include a .h. And in Maine, we hash include the .h for every function we need. Yeah? For every file that contains a function we need. Similarly in all the others. Now, last thing to say about that is, in some of your files, you will write some extra functions that no one else ever needs to know about. So for example, in your Sudoku grid.c, you're writing those functions that we require you to write. You might end up writing a whole lot of helper functions, one called check every cell, or one called clear every cell, or something like that. And that's your own little function that only you need to know about inside Sudoku grid.c. Can you see there's a potential problem? If I later on get your Sudoku grid.c and my test Sudoku grid.c and we compile them together, what terrible thing might happen? I might have used a helper function with the same name. It's not unlikely. In fact, there's very few names and they're pretty obvious for helper functions, so there's a good chance I'm going to have a helper function with the same name. What's C going to do then when it compiles it and it finds one function here with this name and another function here with the same name? It'll be sad. It'll put out that compiler error message, compiler is sad. So how can we make sure that you don't use the same name for a function that I'm going to use for a function? Read the spec. In the spec I could say don't use any functions except the ones I've told you, don't write helpers, but I like using helpers, that breaks things up. I could tell you give them all unique names by writing your middle name in front of every function. Your student number in front of every function. And then it's not going to have the same name as mine, but that's got the disadvantage that all your functions now have stupid names. Better still is, if only we could say you can think of whatever functions you want, but they'll be secret. And no one outside your file will ever be able to see them. If only there was a word in C that meant secret function no one else can ever see. And there is a word. And it goes, secret function that no one else can ever see. It's in Latin. Static. So you put, and you'll see this in the Tutes and Labs next week, you put static in front of all your function declarations, and those functions will be secret and no one else can ever see them. For heaven's sake, don't put it in front of the functions I need to see, like clear cell and set cell and is legal, because then I won't be able to see them to test them. But every extra little function you write, put static in front of it. Does that make sense? Mm-hmm. Question?
I'm assuming that you'd still prototype them locally, but do you have to include static in the function prototypes?
Yes, you can include static in the function prototypes. I'm not sure if you have to, but you should. And you don't put them in the .h file, because then everyone can see them. Yeah, because that'll get embedded in the other files. So you declare in the .h files all the functions you're sharing with the rest of the world. You prototype in your own file with the word static in front of them, all the functions you don't want anyone else to see. Got it? Yes?
What if I want to test my helper functions?
You want to test your helper functions, you write the test for the helper functions inside that file. Inside that file. And that's what I've done. In my test Sudoku grid.h, in .c, I've written a whole lot of functions to test Sudoku grid, and I wrote some helper functions to help me do that. And because I wanted to know my helper functions were correct, I wrote test functions for those helper functions in there as well. Inside test. I don't have a test Sudoku grid.c.
A testing of Sudoku grid that I want to test.
You want to test the helper function. You can test them yourself inside your file.
Yeah, inside the implementation.
But not inside your test.
But not in the test. Okay.
Can I just make, that's a really good question. Can everyone see that? Suppose you've written your own test. Let me say this really clearly because all the words are very similar and I don't want to get it wrong. Suppose you've written your own version of Sudoku grid.c. And in that, you've written some helper functions. And you decide, being a good programmer, you want to write tests for those helper functions. Where should you put those tests? Should you put those tests in Sudoku grid.c, where the helper functions are? Or should you put those tests in test Sudoku grid.c? Tricky question. You might think it's test Sudoku grid.c, but it's not. You test them in Sudoku grid.c because they're secret private functions and test Sudoku grid.c can't see them. Furthermore, it would be mean to put them in this file because then when I use your test file to test your functions and you haven't got those helper functions, she will fail those tests. And that would be cruel because she's not required to write those helper functions. Does that make sense? I want everyone to get that last point because in a way that might be the most important summary point of the lecture. The things that you share with the rest of the world go in the .h file and are public to everyone and are tested in your test file. And the things that are secret and private to yourself go in your .c file. And they're made static so they're secret and they're tested in the same file where you write them. Does that make sense? So there's two sorts of tests. Private tests and public. Oh, private tests, public tests. Okay. Yes, question?
Did you say there are going to be 5 different files that we're going to have to use?
There are 5 different files. Main.c, test Sudoku grid.c, Sudoku grid.c, Sudoku grid.h, and test Sudoku grid.h. Except that, I've already written main.c for you and it's in the lecture notes from yesterday. With the assignment specification, test Sudoku grid.h and Sudoku grid.h I've already written and you use those. And all you hand in are these 2. I lost your eye. Where are you? Yeah. Did that make sense?
Yeah, but another thing about it is if you want to use those 2 files from your into the main,
Yes.
does that mean you have to compile them both as well?
Yes, you compile them all together. So you go GCC, the normal GCC, except instead of just listing one file at the end, main.c, you list them all. So you'd say also Sudoku grid.c and test Sudoku grid.c. Whack them.
What about the file outputs? You have to put more than one file output.
No, there's just one output. What happened? That's a good question. With multiple file compilations, you've split your program over multiple files. And that makes it very convenient to write the program. But at the end, we just want one program. So what it does is it compiles all the things separately. And it'll actually make, just out of interest, it'll make a program called main.o, which will contain all the machine code. C will be converted to machine code. And it'll contain produce a file called Sudoku grid.o. And it will mysteriously also produce a file called test Sudoku grid.o. And then it will do something called linking, which means it'll join all those together, checking hopefully there's exactly one of every function it needs. And it will produce an executable called whatever you want. And in that linking time, it will also link in with a whole lot of other .o files that you can't even see called library.o files. And it'll link in with the library called stdlib.o, and it'll get stdio.o, sorry, and it'll pull out the machine code for printf, and it'll pull out the machine code for scanf. And at that linking time, all the things it needs are compiled together and rolled into one ball, and then given the name that you've given it with the -o. Does that make sense? That's a very good question. So after compilation, have a look, and you should see there's a whole lot of mysterious .o files just floating around that you can delete. Yeah. Now, we have, -2 minutes for just general questions. General questions, yes?
So we write all our functions in the Sudoku grid.c.
You write all your functions in Sudoku grid.c.
How does that link to the Sudoku grid.h? Because in our main, we hash include the Sudoku grid.h.
Yep, Sudoku grid.h would be hash included in all of your .c files. Because those prototypes are needed in all the C files.
How does your main function call on the function?
It calls in the same way you call any function, just by saying the name of the function in brackets. Come and see me afterwards, because there might just be a little misunderstanding. Yeah. All right, good luck everyone. Keep using the forum and I'll see you next week. Yes?
In our test Sudoku, whatever.
Yes.